I want you to picture a scenario. And it's a nightmare anyone who's ever touched a keyboard or a calculus textbook has probably lived through.
Oh, I think I know where this is going.
Right. You're learning a new skill, let's say a new programming language, maybe Rust or something. You've spent hours sweating over some complex algorithm. You're sure you've got it. You hit compile, you're almost trembling.
And the screen just flashes red.
Exactly. But here's the nightmare part. Imagine the compiler. It doesn't tell you what went wrong. It doesn't say syntax error on line 40. It just spits out one giant word, wrong.
Hey, that is the stuff of anxiety dreams. Just a binary fail.
Right. No notes, no helpful suggestions, just fail, and then you're told, okay, do it again.
You'd quit. I mean, that would be completely maddening for a human student.
It would, but as it turns out, that's essentially the status quo for how we've been training some of our smartest AI models.
It is. It's an incredibly harsh, really inefficient way to learn. It's like trying to play a piano concerto, but the only feedback you ever get is a green light or a red light after you've finished the entire piece.
You have no idea if you messed up the first bar or the very last note.
Not at all.
But, and this is why we're here today, that whole dynamic is starting to shift. We're doing a deep dive into a paper that literally just released late January 2026. It's called Reinforcement Learning via Self-Distillation by Jonas Hubotter and his team.
And this is a really significant piece of work. It feels like one of those papers that just unlocks a door we've been banging our heads against for a while.
So the mission for this deep dive is to unpack how these researchers figured out a way for an AI to, well, essentially act as its own teacher.
Exactly.
To turn those cryptic error messages into actual light bulb moments without needing a human standing over its shoulder grading every single step.
It's a fascinating pivot. We're moving away from what we call scalar rewards, that simple pass-fail, and toward leveraging the rich textual feedback that's already there. And honestly, it addresses a bottleneck in machine learning that's been holding us back for years.
So, okay, let's set the stage a little. I think most of us assume that if an AI is learning, it's getting detailed feedback. You know, like, good job on the logic, but your syntax here is off. But you're saying that's not really the case.
Not in the standard pipeline, no. Especially not in these final stages of training reasoning models. I mean, let's look at the current industry standard. Reinforcement learning with verifiable rewards, or RLVR.
RLVR. Right. We hear that acronym a lot. That's the engine behind so many of the reasoning models we see today, yeah.
Correct. And the whole premise of RLVR is actually very simple.
Yeah.
You give the model a task where the outcome is objectively measurable.
A math problem, a coding challenge.
Exactly. The model generates a solution. We run it. If it passes the test cases, the model gets a reward, let's say a +1. If it fails, it gets a 0.
So it's strictly binary, pass or fail.
It is. And while that does work, eventually, I mean, if you do it millions and millions of times, it creates what the paper calls the credit assignment bottleneck.
Credit assignment bottleneck. Okay, let's break that down. It sounds a little like a manager not knowing who to promote because a project failed and they don't know whose fault it was.
That's a perfect analogy, actually. Imagine a team of, say, 500 people works on a project. The project fails. The CEO just walks in and fires everyone.
That seems unfair and really unproductive.
Exactly. So in a neural network, think about an LLM generating a solution. It might output 500 tokens. That's lines of reasoning, code, syntax. If that final result is false or error, the model just gets a 0.
But it has no idea which of those 500 tokens was the problem.
Precisely.
Did I fail because I misunderstood the prompt way back at token 10? Or did I miss a semicolon at token 490?
Or did you hallucinate a library that doesn't even exist? The credit for the success or the blame for the failure is just impossible to assign to a specific step.
So what does the algorithm do?
The standard RL algorithm just suppresses the probability of that entire sequence just a tiny bit. It basically throws the baby out with the bathwater.
And then it just has to blindly try again, hoping to stumble onto a path that gets that +1.
Which is incredibly computationally expensive. You're just burning through GPUs, guessing and checking until you get lucky. It's brute force masquerading as learning.
Okay, so that's the problem. But this is where the paper makes that crucial observation. In the real world, especially in coding environments, we actually do get feedback.
The compiler screams at you.
Right.
Exactly. You get a syntax error, unexpected token,
Yeah.
or an index error, or a physics simulator returns collision detected. That is rich semantic information. It points to the specific location and nature of the failure.
But standard RLVR just ignores that.
It effectively treats it as noise.
Yeah.
It sees the error message, says, well, that's not the right answer, marks the attempt as a fail, and moves on. It leaves all of that useful intelligence on the table.
That feels like such a monumental waste. It's like a student getting a graded essay back, seeing the teacher wrote a whole paragraph of detailed feedback at the bottom.
And the student just rips that part off without reading it, looks at the F, and tries to rewrite the whole thing from scratch.
That's the perfect analogy. You're ignoring the roadmap to the solution. And that is what this new method, Self-Distillation Policy Optimization, or SDPO, is designed to fix.
Yes.
SDPO. Okay, let's get into the mechanics here. The name self-distillation sounds a bit like a chemistry experiment. It implies the model is extracting something from itself. How does it work?
The core concept is all about tuning the model into a self-teacher. The goal is to take that rich textual feedback, the error message, and convert it into a dense learning signal that updates the model's policy token by token.
Dense, meaning it tells you a lot more than just good or bad.
Exactly. It provides a gradient of direction for every single step of the thinking process.
Okay, so walk me through the loop. The model writes some bad code, the environment throws an error. Then what?
All right, so step one, the model attempts a task. Let's say it writes a Python function. It fails. The environment returns index error. List index out of range.
Classic. The classic off by one error. We've all been there.
We all have. Now, in the old way, that's just a zero, a fail. But in SDPO, the system takes that error message and it appends it to the context window. It feeds the error back into the model.
So it forces the model to look at its own mistake.
Yes, and this relies on a specific property of these big models.
Right.
They're generally much better at debugging than they are at generating perfect code from scratch.
Right.
If you show an LLM its own bad code in the error message and ask what went wrong, it can usually figure it out.
Right. It gets that 20/20 hindsight. It looks at the error and goes, oh, obviously I should have stopped the loop one step earlier.
Exactly. So SDPO treats the model conditioned on the error message as the teacher model. This teacher looks at the mistake and says, in terms of probability, okay, given this index error, the next token should have been a generic loop, not a specific index.
I think I'm getting it. It uses the smarter, in-context version of itself to teach the dumber, original version of itself.
That's it. It then calculates the divergence, the mathematical difference between what the base model did do, which was the mistake, and what the teacher model, the one looking at the error, says it should have done.
And it updates the weights of the base model to close that gap.
To minimize that difference. So it's taking that hindsight, that realization of the error, and distilling it into foresight. It's updating the probability so that next time it doesn't need to see the error message to know not to make that mistake in the first place.
That is really clever. It completely avoids the need for a separate reward model or a human labeler. It's a closed loop.
It is. The model fails, learns from the failure message, and updates itself. And it's so much more sample efficient. You don't need to run 1,000 random attempts to find a winner. You can take a single loser, analyze why it lost, and squeeze all the learning juice out of that failure.
Squeezing learning juice out of failure. I like that. But okay, theory is great. Let's talk results. Does this actually translate to better performance?
Oh yeah, the results are robust.
Yeah.
They tested this across several domains: scientific reasoning, tool use, and specifically competitive programming on a benchmark called LiveCodeBench v6.
LiveCodeBench, that's the one that uses real LeetCode style problems, right? It's not just multiple choice.
Correct. It executes the code against hidden test cases, so it's a really rigorous standard. And SDPO showed significant improvements.
Like what?
First, in sample efficiency, it learned faster, requiring fewer training steps to get good. But it also achieved higher final accuracy compared to strong RLVR baselines.
So it learns faster and it ends up smarter.
Yes. But here's the twist.
Yeah.
This is the part of the paper I found most surprising, where it gets a little mind-bending.
Okay.
They also tested SDPO in environments that don't provide rich error messages, environments where you only get that binary pass-fail.
Wait, hold on. I thought the whole point was using the rich textual feedback. If you only get a fail with no explanation, how can the model self-teach? Where's the teacher model coming from?
This is where the self-distillation concept gets generalized. If there are no error messages, SDPO just flips the script.
How?
It uses the successful attempts as the teacher.
Run that by me again. How does a success teach a failure?
Okay, so let's say the model tries a complex math problem 10 times. It's probabilistic, so it tries slightly different reasoning paths each time. 9 times it fails. One time, maybe by chance, it gets the right answer.
The lucky strike.
Right. In standard RL, you just reward that one path and pretty much discard the others. But in SDPO, the system takes that one successful path and treats it as the teacher.
Ah, I see.
Compares the 9 failed attempts against that one successful one. It uses the success to generate the correct probability distribution for the failed scenarios.
So it's comparing its best self to its worst self.
Exactly. It uses its own wins as the answer key to correct its losses. It's effectively asking, hey, look at this trajectory where we got it right. Why did the other 9 deviate? What did we do differently here? And it distills that successful logic back into the base policy.
That's fascinating. It implies that even in those binary environments, we aren't using the data fully. We're just reinforcing the win, not actively correcting the loss using the win as a reference.
And the paper confirms this. SDPO outperforms the baselines even in these scalar feedback environments. It's just a better way to extract signal from data, whether that signal is an explicit error message or an implicit comparison to a successful run.
It turns every single rollout, win or lose, into valuable training data.
That's the essence of distillation. You're taking a lot of noise and boiling it down to the pure signal.
Okay, there was another metric that jumped out at me. Test time efficiency. Usually when we talk efficiency, we mean training costs. But this is about when the model is actually being used.
Yes, and this is crucial for real-world applications. I mean, think about how we solve hard problems with LLMs right now. A common technique is best-of-K sampling.
Which is just a fancy way of saying brute force. Ask it to generate like 100 answers and pick the best one.
Exactly. Or multi-turn prompting. Are you sure? Check your work. Both of those eat up tokens and time. It's slow for the user and costly for the provider.
So what does SDPO do differently at test time?
The researchers found that because SDPO learns from its mistakes so effectively during training, the resulting model is just much sharper. The statistic they give is that SDPO achieves the same discovery probability, the chance of finding the right answer, with 3 times fewer attempts than standard models.
3 times. That's not a small improvement. That's a fundamental shift.
It is. Instead of needing to generate 100 code snippets to find one that works, maybe you only need 30. If you're a company running millions of queries a day, cutting your inference compute by 66% is, well, it's massive.
It changes the entire viability of using these models for complex tasks. It's the difference between a product that costs 10 cents per query and one that costs 3 cents.
And it suggests the model isn't just memorizing. It has a more robust internal policy. It's less reliant on getting lucky with a random seed. It actually knows what it's doing, in a sense.
It feels like we're seeing a real shift in philosophy. For a long time, the approach was just more data, bigger models. This feels like better digestion.
That's a great way to put it. We're moving from just the quantity of data to the quality of feedback processing. We're moving towards AI that is more autonomous in its own learning loop.
Let's double click on that autonomous part. Because right now, RLHF, human feedback, is the gold standard. We hire armies of people to rate model outputs. Does SDPO threaten that model?
I wouldn't say threaten, but it solves a major scaling issue. Human feedback is expensive, it's inconsistent, it's slow. And for things like advanced coding or quantum physics, humans might not even be fast enough or smart enough to grade it accurately.
But a compiler is instant. A physics engine is instant.
So if the model can learn from the compiler directly using SDPO, we remove the human bottleneck. We are entering an era where the model can look at the environment, the tools, the code interpreters, and learn directly from the rules of the world.
It's turning the runtime environment into the classroom.
And the teacher is just the reality of whether the code ran or not. It's very grounded.
It's a move towards self-correction. I mean, I think about how I learn. If I touch a hot stove, I don't need a tutor to tell me that was bad. The pain, the error signal is immediate and rich. I instantly update my policy. Don't touch the red glowing thing.
And you don't just learn don't touch. You learn about heat transfer, about safety. You generalize. And that's what we hope SDPO is doing here, building a generalized capability to reason through errors.
So if we project this forward, we have models that can write code, run it, see the error, understand the error, update their own internal probability map, and then try again, all within seconds.
It just accelerates the scientific process. Imagine a model trying to find a new protein structure. It simulates a fold, the physics engine says energy level too high, and gives a readout of where the atomic clash happened. The model uses SDPO to learn from that clash and adjust its hypothesis.
It's acting like a scientist, not just a library.
It helps bridge that gap between memorization and real reasoning.
That's a compelling vision. We're moving from the frustration of that blind wrong stamp to a system that says, okay, I messed up, here's exactly why, and here's how I fix it. It's efficient, it's autonomous, and honestly, it's a very mature way to learn.
It validates the idea that failure isn't just a lack of success. Failure is data, if you have the right mechanism to decode it.
I think we could all use a bit of SDPO in our own lives, turning our own error messages into policy updates. So, here's a thought to leave you with. We've talked about AI acting as its own teacher, analyzing its mistakes to improve. If these models are getting better at this retrospective analysis, at understanding why they failed, how far are we from a model that doesn't just solve the problem, but fundamentally understands the purpose of the problem?
That is the big question, isn't it? Are we just simulating a better student, or are we on the path to creating a true scholar?
Something to mull over the next time you see a 404 error on your screen. Don't just get annoyed. Ask yourself, what would my inner SDPO do with this?
I love that. Optimize your own policy.
Thanks for diving in with us today.
Always a pleasure.
We'll catch you on the next deep dive.